All right. So let's introduce to you the pioneers. All right, everybody, pioneers. All right, I've got everybody's attention. Who am I missing? Whose attention am I missing? Okay, we got everybody? Okay, good. So I want to tell you that why this is such a special night for us up here, because all these pioneers are here for you. They're here to honor you because you are the future. No matter what country you come from, you are the future of mankind and the future of mankind going into space. So, as we go forward, I want to talk again. There's been some questions again about questions and answers. So you all have your card. I want to go over the rules again. Everybody got their card? Let me see the cards. 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 Okay, very good. We want the question, we want the name, and we want your team name, okay? Is Penny ready? Where's Penny? I see Vince. Do you have your mic? Vince has his mic.
Yes, I do.
You do?
I do.
You do.
Indeed.
Very good. Very good. So we will, as soon as we get Penny back, we'll do that. But social media, I love you, but the book is for the competitors. Is the book for sale somewhere? So, hey, this is a great opportunity. You all need to tell the Space and Rocket Center they need to put this book on for sale here, because we're trying to get that done. The book is Amazon, right? Amazon.com. You can get it at Amazon.com. Do we have anybody from California in the room? Okay. I was at the Endeavour Space Shuttle last week, and they are selling the book at the Endeavour in front of the Space Shuttle. So if you go see Endeavour, you can also get this book. And what's cool there is they're selling little Legos. They actually have a Lego of the lunar modules. So I'm like, you can get the book to figure out how to build it, and then build it. I think that's pretty cool. Okay. As soon as you sign that one and he signs that one, we're going to start. Okay? And as soon as Penny shows up. So Vince.
Yes.
What?
Yes.
Okay, you will be solo until Penny returns. Okay. You okay? Okay, so we're going to start with the introduction of the pioneers. And then once the pioneers talk to you and give you some of their thoughts, we're going to open up to the competitors to ask their questions. And once the competitors have asked all their questions, then social media. Do you have questions? Because I've got time for you built in to ask questions. Okay? So, are we ready? Penny? Okay, Penny's going to get back in the back. Everybody knows Penny? Say hi to Penny. Hi, Penny. And then Vince back in the back. All right. See, it's a pizza party, right? You're supposed to have a good time. Okay. So, Mr. Morea, sir, that's you. That's you. So the first thing I'd like to ask you as part of my question is, you had 17 months, and in the movie, you recount the fact that you had Dr. Von Braun call you up. Now, you were originally, as I understand it, responsible for the program management of the biggest, baddest, most awesome rocket engine ever put on the planet Earth, the F-1 that powered the Saturn V first stage. Is that correct, sir?
That's correct.
That is correct. So
That's
Mr.
correct.
Thank you, sir. So when you see those 5 glorious F-1 engines at the bottom of the Saturn V, Mr. Morea and his team right here.
Thank you.
So clearly, sir, Dr. Von Braun must have thought that this Lunar Roving Vehicle project was pretty darn important if he's going to put you his ace rocket engine guy in charge. And I'm wondering if you could talk about the fact that he only gave you 17 months and tell me about program management of that 17 months, and then explain the tie. I need to understand the bow tie.
Where would you like me to begin? So much to say, so little time.
Okay, go ahead.
I guess I'd like to say that as I look across this audience tonight, I realized that I too was your age many moons ago. But I know the kinds of things you're going through. Unfortunately, today, many of the young folks have a pretty bad reputation. You text while driving, you drink a lot, you smoke pot and all this good stuff. But I have to tell you that the group that's here tonight represents the best that there is out there in the world. It used to be just this country. I used to just say in America. But we have young people here from all over the world, and you are the best, let me tell you. And I won't miss a single one of these as long as I'm alive, because it is so important to realize that you will make this world a better world in the long run. And so now I want to tell you how I got into this business. Okay, like you, I started out in college. In fact, my history really goes back before then. I had a great appeal for the world of aviation, and the place that I grew up, as you can probably tell from my speaking tonight, I went to a school called Brooklyn Technical High School in Brooklyn, New York, okay? And I took a course there called the aeronautical course. They taught electrical engineering courses, and they taught architectural. They had a college preparatory course. I took the aeronautical because my plan was to become a pilot someday with the Air Force. However, with all the studying that I did, my eyes didn't support my getting into the service. And so I went on and became a mechanical engineer at CCNY in New York. And I see someone's fist just went up. Is that because you know about CCNY? Okay, right. Well, I got a mechanical engineering degree, and also I participated in the ROTC program at CCNY. And I always take credit for those of you who happen to remember Colin Powell, who used to be Secretary of State. Colin Powell went to CCNY, and he too was in the ROTC program. And I always take credit for everything he learned in the military. Okay, now I never met the man, but we went to school together, and we were in that same ROTC program. And I was ahead of him by 2 years. Okay, that's why I take all the credit that I do. Got my commission and went into the service. I was commissioned second lieutenant in the Army Corps of Engineers, combat engineers. And I took a job with North American Aviation. None of you would remember that. It was way before your time, and the company doesn't exist anymore. But they were eventually bought out by Boeing, and there was a number of amalgamations that took place. And I guess today, whatever's left of that company is part of the Rocketdyne Pratt & Whitney organization. But anyhow, I took a job with them, and I had the good fortune at that time to be assigned to a project called the Navajo program. Now, some of you may have seen that in the history books, but it was the first cruise missile that was truly intercontinental. It had the capability of delivering an atomic bomb within 300 yards of its target in downtown Moscow. So it was quite the project at that time. And it was a Mach 3 airplane, basically. It was a cruise missile. I did some of the work on that relative to the wind tunnel model work. At those high Mach numbers, Tullahoma, Tennessee was kind of the one place we could do wind tunnel work. So I worked on that for about a year when I finally had my orders to come into service and serve my 2-year commitment. In that 2-year commitment, I was my MOS was changed from combat engineer to ordnance, Army ordnance, because of the work that I did on the Navajo program. They felt I was better suited in the world of the ordnance and missiles. And they knew that certain work was going on down in here in Huntsville with the Von Braun team, and I was assigned down here to be a member of that team. And I arrived here in June 10th, 1955, with a wife and a little baby daughter, and went to work for Von Braun and his group. Now, to tell you the sort of leader that Von Braun was, I mean, we hear a lot of things about Von Braun, but first and foremost, he accomplished most of what he did because he was such a great leader of people. He interviewed me as an individual when I reported for duty to his organization, and he found out that I was a mechanical engineer, and he told me, Sonny, that's what I was known as, I'd like for you to go out and interview all of my laboratory directors, find out what we do in these laboratories, and I want to assign you to wherever you think you can make your best contribution and be most interesting. So I did that, and how many of you will have that opportunity or have had that opportunity for someone to ask you, where would you like to go to work for me? Okay? Well, that's because I was working for the greatest leader of most men, okay? So I picked my field. At that time, it was heat transfer and thermodynamics, and went to work for one of his 131 Germans that came over with him in the paperclip operation. And it wasn't but 6 weeks later that the number 3 man at the Army, at that time was called the Guided Missile Development Division here on post. And I got a call from his number 3 man. And he said, by the way, he says, you're from New York, aren't you? And I says, yes, sir. And he says, well, you know, there's a company up in New York called Ford Instrument Company that provides the servo mechanisms to steer the Redstone missile. And these are jet vanes that sit in the flame itself, and by moving the jet vane, you can steer the missile. He says, and they're having all sorts of technical problems. Would you like to do some liaison work with us with the Ford Instrument Company? I said, yeah, of course. And so that's how I really got into the field of propulsion. For a while, I spent time in this servo mechanism world of astronautics and stuff like this, but ultimately I ended up getting into the propulsion project office of that organization. And in there I worked on the RL-10 specifications. I worked on the development of the H-1 engine as a project engineer in the project office. And about the time that the president made the announcement that we ought to go to the moon in this decade and return man, was when they were looking for people that had certain flexibilities and experience to lead teams on these new projects that were coming along. One of them was the F1 engine. And I was asked, and I was pretty young to take on that, assume that duty. I took on the development of the F1 engine. There was also the J2 engine existed at that time as a project. And there were a couple of other engines that were being brought about. But the F1 was the big one, and I had the task of leading that team, that project team, for a number of years, 6 as a matter of fact. I took it through the phase of qualifying it for manned operation. Excuse me. At the conclusion of that, I guess I was promoted back or up to being a program manager for all the engines. And that lasted about 6 months. We had a flight. Oh.
You okay?
No.
You're not okay?
No, hold on. I got a cramp. Bad cramp.
A leg cramp?
Yeah. Oh, it's just right in place.
Well, you'll have. That's good. You all right?
Yeah, I think so. I'm sorry, I had a leg cramp.
We're okay,
Any of you
people.
ever had
Nothing
any of those,
to
you know
fear.
what I'm going through right now.
Is it the excitement of the moment?
Oh, yes. I just got to calm down, I guess. I'd like to, but I can't, so I'm just going to... I can pull your chair back and help you. I'm not going to fall at that point. I'm sorry, I'll be back with you in a moment here.
Would you like me to have Skeet talk while you're working it out?
Yeah, that'd be fun.
All right, so we're going to go to Skeet.
Well,
Okay, so Mr. Vaughan, while Mr. Morea is working it out, your responsibility was to figure out lunar soil, and you were to figure out how the lunar rover worked in the soil, and you were also, can you tell us something about that part of the thing, and can you tell us about the overall development of the lunar rover, and can you tell us about that, a little bit about that unit as well?
well, actually, when I came to Marshall, I actually came to the Army Ballistic Missile Agency in 1956 and got a chance to work with the Von Braun team as a member of that team, and then we went into NASA in 1960, and later on in my career, I was very fortunate to be assigned to work in an environmental design group where I was a mechanical engineer, and I had to come up with some ideas on what we thought the lunar surface might be like. And this was in 1964. And when back in those days, when we would look at the lunar surface, the best resolution we had from the Earth on the size of the craters was about 900 feet. So the problem we had was where are we going to land on the moon? So the idea was to select those areas which look like the flat areas, which are like the big Maria on the moon right now. You see, when you go out at night, you can see the Maria, the big areas. Then later on, about 64, we got some real good high-resolution photographs of the lunar surface from the lunar orbiter. And from that, I was able to determine the the size of craters and the block distributions on craters, and some idea of what the soil might be like because of the way the light was reflected off the soil. We did a lot of work with the lunar environment by making measurements from the Earth of what the temperature of the moon was. So in reality, when my job at NASA was to come up with an environmental design criteria document which could be used for the rover design. So I had to come up with a radiation model to damage electronics, a temperature model, and then also a lunar surface operations model. And that was called Lunar Design Criteria, which is part of the document which was used to design the rover.
Excellent. Now, do you remember the history of that particular rover over there?
No, I don't know that.
Okay. So, I'm going to go ahead and go to Mr. Mike Vaccaro, who was Cruise Systems. So, Mr. Vaccaro, what I'd like to know is, now, you're in this picture. You're in this picture. Are you the front guy? Are you the guy in the back?
Yeah, I'm the short one there.
You're the guy in the back. All right. So you've worn the Apollo suits. You've worn the Apollo spacecraft suits, and you also flew the KC-135 Vomit Comet. What, the astronauts couldn't do it? They were scared, so they put you in. You were the brave man first? How does that work?
What was your last thing you asked me?
So tell me about your crew systems
Okay.
and the development using the KC-135.
Right. I don't know whether you all have heard the name of engineering called human engineering, or human factors engineering. Well, my degree is in mechanical engineering. I, just like Mr. Morea, I'm from Brooklyn also, only I went to a different university. And by the way, CCNY is now CUNY. Since Mr. Morea and General Colin Powell there went, I think that was one of the reasons they changed it to a university. It's not a college anymore. But when they went to college way back, it was just a college, CCNY, City College of New York. And I was the competitor. I went to the competitor university, New York University, and it was the engineering school was located in the Bronx. One thing about the the different boroughs of Brooklyn, when you say Brooklyn, it's just plain Brooklyn. When you're talking about the Bronx, it's the Bronx. You never say the Brooklyn. You learn something. See? Anyway, I started working for NASA right out of the Air Force. I had put in 8 years on active duty as a lieutenant and then a captain. And because of my degree in mechanical engineering, I felt I was spinning my wheels staying in the Air Force. I thought I'd be up at Wright-Patterson Air Force Base working on R&D projects, but that wasn't what the Air Force had in mind for me. I was an ECO officer, electronic countermeasure officer in SAC. And it was the same thing every day. And that was when the Cold War was hot. And the B-29s were flying, and then the B-47s came in to operation, and after the B-47s, the B-52s. I don't know if it was my luck or my bad luck or my good luck, but I got hurt in the service, in the Air Force, and I had to go to the hospital and spent 18 days in traction. I messed up my back in a vehicle accident, not an airplane, hard landing. It was in a what they call a weapons carrier towing some nuclear weapons to the flight line. Luckily, it was on the way back that the vehicle turned over, and I got thrown clear, but it landed on my back, and I had a lot of trouble, and I still do. But anyway, moving right along. In 1960, I applied to be relieved of active duty. I was a regular officer in the Air. I had taken ROTC, and I graduated as a DMG, a Distinguished Military Graduate, and that made me eligible to get a regular commission in the Air Force. And anyway, as I said, 8 years later, 1960, I decided, after sending in my resume to the NASA Marshall Space Flight Center here in Huntsville, I got a word back right away. Yeah, please come for an interview. We need engineers badly. I did, and I was hired. And my first job was not in crew systems or manned systems integration or man engineering. It was working on a drawing board, laying out these big stainless steel suction lines and bellows that Mr. Morea's engine hooked onto. They went from the engine to the RP-1 tank and the LOX tank, rocket propulsion fuel, and the liquid oxygen tanks. And the reason we needed these big, huge suction lines was because the engines all gimbaled except the one in the middle. So you had all these engines which were controlled by gimbaling these F1 engines, each one with a thrust of 1.5 million pounds for a total thrust of 7.5 million pounds. And these big suction lines and bellows had to withstand some tremendous loads. But I got a little tired of that, like I did 8 years on active duty with the United States Air Force, and I was looking for greener pastures. That's when Marshall Space Flight Center in the early 60s had aspirations of training astronauts here in Huntsville. And they formed a branch which had initially about 40 people. half of which were engineers. That was called Manned Systems Integration. And we said, we've got the personnel. Some of us went up to the University of Michigan in Ann Arbor, took some courses in human engineering. Some went to Penn State to study human factors engineering. But anyway, we had the personnel and we had them trained. And those that were Marshall Space Flight Center that came back from the training that they got at these universities, different universities, were training other engineers. You know, we were in competition with the Johnson Space Center in Houston, Texas, Clear Lake. But however, Dr. Von Braun gave us the green light to go ahead because we were studying this new space station, Skylab. You might have heard of it. And we needed some trained human factors engineers that can get into simulation. You can do all the calculations you want, but at the end, you have to simulate what the astronauts will be doing in space. That was when Marshall Space Flight Center got into the neutral buoyancy simulation work. We had a tank here on Marshall, 40 feet in diameter and, I don't know, about 40 feet deep. And we did a lot of simulation underwater, which simulates weightlessness. And you can't splash around in the water. You have to move your movements have to be very slow. And because of the water resistance, and you can get some simulation that you'll find in true weightlessness. However, the spacesuits, we were wearing spacesuits that looked just like the lunar mission spacesuits, only they were designed for water. And before they'd let you in the tank to go through a simulation, a particular operation, the suit, you in the suit had to be balanced. We had all these little weights all over the suit, legs, arms, torso. And you can go in the water and just lay there motionless and you won't turn over, you won't sink, you won't rise to the. So it took a little while to get those suits balanced just right. The better you had them balanced, the closer is the simulation to 0G. And the other type of simulation we used a lot was flying the Air Force KC-135. We used to fly out of Wright-Patterson Air Force Base. And some of you may know a little bit about 0G flying with the KC-135, where you can get 30 seconds of weightlessness. And your pullouts when the KC is diving, and then it pulls out and it's ready to climb again. You're experiencing 2 to 2.5 Gs. So it was quite interesting and quite exciting. However, a lot of people, including astronauts, who didn't have a good, strong stomach, didn't come down empty-handed. They were carrying a bunch of barf bags in their hand. But one thing stands in my mind. We had a mock-up of the Lunar Rover. It had everything, but you couldn't drive it. It was fixed in the KC-135. And I flew with John Young, who was on Apollo, I think 16, if I'm not mistaken. And with him was Charlie Duke. But John Young was very inquisitive. I was a test conductor on a couple of flights with him, and I'd always show him the test procedure, and he'd look at it and just toss it away. He was going to do what he wanted to do, not what the NASA engineers wanted him to do. And one of the things was the ingress, egress. He thought he'd be hopping in and out of the LRV a lot. However, he found out by loosening up the seat belts, that he can lean over and pick up things on the lunar surface. He had to lean pretty far over, though, but he learned that from flying with us. And one thing you have to realize, the moon is 1/6 G. So the pilot of the KC was not flying 0 G, he was flying 1/6 G. Because when John Young got out, he didn't want to be floating, he wanted to be walking around so that he knows what it feels like, or it's going to feel like when he's on the moon. And it's a little harder to hold it at 1/6 G. If you ever get the opportunity to fly on one of these, the nickname is Vomit Comet, I guess you know. If you ever get the opportunity, do it. We even had Von Braun up there for 10 parabolas, and he loved it. He really did. We had him in the neutral buoyancy facility. He tried that out. He wanted to know about everything we were doing. Getting back to the LRV, what I got involved with, I believe, was very important because the astronauts were having a problem with the hand controller. If you know anything about pressure suits, full pressure suits, like the Apollo, they're pressurized at 3.7 psi, 100% oxygen. And that includes the gloves. And that puts a strain on your fingers. You can't hold a fist very long without your hands just getting very tired. So we tried all different type of hand controllers. We had the pistol grip, we had circular controllers. We tested a lot of them. A lot of suggestions from the engineers at NASA. We made those hand controls. And after all these were turned down, were not acceptable to the astronauts, we finally came up with this T-handle. T-handle. You don't have to keep your hand in a closed position all the time, and you can still steer. And as some of you probably already know, that it was a single hand control. Your throttle, your brake, you turn to the right, turn to the left. Is the way it drove. And the astronauts, when they drove it on the moon, they were pleased with it, they said. That T-handle worked out, and I have to be very honored that I was involved in the development of that T-handle. And one of the ways I knew it was going to work was because I put many hours on a driving simulator, a video picture of the moon, which simulated what the LRV would do in 1/6 G. And you still, going over bumps and down into craters, and you still have to be able to steer that vehicle, because you certainly don't want to flip it, and it's easy to flip in 1/6 G, as you know. And I'll just mention one more thing, and then I'll pass this mic along. When Dave Scott got back from his Apollo 15 mission, he sent for the engineers that designed the seatbelts. And I thought he wanted to see the engineer that designed or helped design those seatbelts and congratulate him and thank him, But it turned out just the opposite. he rode the riot act with me. I mean, he told me that they were the worst seat belts he had ever had in his life, and it took like 3 minutes to unlock them and about 5 minutes to put them on. See, you cannot see your tummy when you're wearing that spacesuit and you got the helmet on. You're dependent strictly by feel. And he said he had the toughest time, and he proceeded to tell me an astronaut's time when he's on the moon is $50,000 a minute. You know, I thought he was going to ask me to write a check or something like that. But I got the word. I mean, loud and clear. Came back here to Marshall, and we redesigned those seat belts. One of the problems is, you know, when the seat belt falls, when you take it off, you can't see it again. So what we did, one of the innovations was we had one of these old horse and wagon buggy whips device. So it was always within sight, and the astronaut could grab it and fasten it. But anyway, they were pleased on Apollo 16 and 17. There was no more. We want to talk to Mike Vaccaro up there at Houston about those seatbelts. But they did praise the T-handle, and they had no problems with it. They didn't want it redesigned. I think I've talked long enough, and you know, it's been a long time since I was involved in the development of some of the human engineering for the LRV. So a lot of information, a lot of facts slipped my mind, but maybe when you ask a question, it might refresh my memory. I'm passing the mic along to Ron Creel.
So before Mr. Creel starts, I want to point out that T-handle's over there. So if you've not had a chance to see it, it's over there. In fact, because of the position that it's in, you can actually look. Normally when it's deployed, it's harder to see, but since it's kind of in its stow position, you can actually see all the inner workings of underneath that T-handle. So make sure you see that before you leave. Now I'm going to go to Mr. Creel. Mr. Creel wants to talk about, he's a thermal engineer, but he wants to talk about telling you about what it took to get that rover from Cape Kennedy to the moon.
Thank you. I'll be quick because I know we want to get to the questions. I wanted to point out a couple of things to y'all. You've probably wondered about this model sitting up here. This is a good old Revell model that I put together and used in real time. It's got a little rover folded there, and I've been talking to Bob Elliott over here from Thermal also for Boeing. We had a plan that on the way to the moon, go ahead and show, Mike, from the Earth to the moon. The whole scenario there.
Ron, before we do that, can I make a point on this picture? Can we go back to that picture for a second? I'm sorry. This is important. This is cool. This is worth your time. See, do you see Ron there? You see the picture in the camera, or you see the picture on the TV screen? That's live.
Oh, yeah.
That's live.
Right.
I just think that's cool. So anyway,
and also notice the teletype. That was our input device for the computer, was through a teletype. Y'all have much more advanced systems, but what I was going to mention to you, Bob's very familiar with this, that on the way to the moon, we were supposed to barbecue the assembly as it went up there. Well, on Apollo 17, for example, they came out of that barbecue in the worst possible attitude. Here's the little rover folded up, and they came out. So I would get each morning, I would go up to 4200, and there was a Tel-X waiting for me that a fellow out in Houston had taken and put down. It was in quaternions, if y'all ever used quaternions. I converted it, and I said to my boss, Hugh Campbell, I said, something's going wrong here. They're not barbecuing. And he says, no, they wouldn't do that. Well, they did. We got to the moon. All the wax was melted in the wax tanks, and we were 95 and 110, so they had to open up the covers during the EVA. I was also going to point out to you how much advances you have nowadays with PowerPoint and all your plotting. This was our mission support book. You see all the hand plots in here that we did up? It was amazing to me that you had to go back in here and derive everything. We had computer models, but the computers were big, cumbersome. The computer would fill this whole room back in those days. But I'll just give y'all a couple of examples there, and y'all can ask questions later. Let's get on to Bob. He's going to talk a little bit about the tape. We had a thermal problem on Apollo 15, and Bob was instrumental in getting that solved.
I really don't have that much to add to what Ron said. There was kind of an interesting project. The whole trick was to find heat sink capacity on the structure and on the components of the thing, and then to make the most use of them as a place to store the heat for while you're in operation. Trying to get it there was part of the trick, because everything that we plotted up was for do a barbecue mode all the way from Earth to Moon, and the first thing they did when they got out of Earth was stop the darn thing so they could look back. So we all threw a fit, but it worked out in the long run, and it worked out quite well. I guess the one thing that amazed me the most about the whole project is the technology and the equipment that was used to build this thing that worked the first time. We had slide rules and hand calculators instead of the modern computers and all. But then some of it was trial and error. But in the long run, everything seemed to work out fine. I'm not going to use this. I went to the final design review for the Lunar Rover up in Washington, D.C. When I got back, my managers wanted me to write a trip report and explain what happened. So I wrote them up one, and my first line said, nobody asked me anything, and my second line said, I didn't volunteer anything, and I signed it, and that was it. I'll pass it on.
Now I want to speak to Mr. Knickrehm for just a second. This is really special for him to be here. In my career, I've had a little bit of experience with something that maybe some of you might have heard of, GPS. Who's heard of GPS? Anybody heard of GPS? Global Positioning System, maybe? So we all know how important GPS is. Well, there is no GPS in 1971, and there certainly is no GPS on the surface of the moon. And, as I think that we'll talk about, there's no magnetic field on the moon. How the heck do you navigate that sucker on the moon, not get lost, can't use a compass, and no GPS?
Well, first of all, I'll mention to you young engineers out here, when you get there, when you have a better idea, tell somebody, because it just may be a better idea. His first thing he asked was, how do you know where you are on the moon? First of all, even in them, we knew where the sun was shining every day on the moon. If you look at the sun's shadow, you can then plot, if you have all the proper equipment, exactly what direction you're facing on the moon. So from that, you can determine a north. Now, if you want to know where do you go from here, if you had a fancy navigation system and lots of computers and all that, you could do that. But that would weigh like 100 pounds. What was our budget? 10. 10. Now, if you take 10 pounds, what can you do with 10 pounds? One, you take some small magnets on each wheel and you count how many times that wheel turn around. Two, you count how many parts of that are in your north direction and how many in east direction. Of course, it's minus west and minus south, so that's simple. So it takes some counters, it takes some kind of set. Now you ask, what happens when I turn a corner and the wheels are going different directions? Easy. You count the third fastest wheel, and then you'll null out the one that's going to be dragging, and you end up with, if you reset every counter after the third count, it will come out exactly like you have. If they're going the same speed, it works out just the same. If they're turning, it corrects. Now, you want to know, why do you come up with that? Simple. The heavyweight, this cheap, well, the lightest navigator they had at that time was in an aircraft that flew fighter missions. and it weighed close to 100 pounds. And that had lots of accelerometers, lots of gyros. Now, on the moon, you take one gyro and you set it for the north, which you now invented because you have a shadow, and you call that north. And then you just put it in a gyroscope that's spinning. It will then retain that for the length of time they'll be traveling. And if you take and vector your direction on your wheel counts off of the direction from the navigator, then when you get there, you just look at it and it tells you which way to go back. You turn your compass till it points in that direction and you go back. And as far as they're concerned, it was north and south. Was it precise? Maybe not. We'll never know. But they always got back right where they started from. Within the worst error they had anywhere, anytime on the moon after they plotted out when they got back was 1/10 kilometer. Well, you can see the little Rover from there. All they need to do is get back so they could fly. So we didn't know much. Now, I'll tell you a little bit about me so you guys out here can think about it. I didn't go to a big fancy university. I went to a small college called Christian Brothers. We're just starting up, and they did not have all the equipment and labs and things that they needed to get started up. So we invented a lot of things along the way in school. They stressed the basics. I learned all the basics there were to learn. So I was good at what I did. Now, it turns out when the people from a company called Sperry Gyroscope come in here from New York, and they went into Memphis at Christian Brothers and said, I want to interview some people. And so I was sent down to be interviewed, and we did through the standard things you do when you do an interview. And we got done. Why, the gentleman doing the interview said, wait a minute. He said, I have a problem I ask everyone to do before they leave. And I said, okay. So he handed it to me, and I looked at it and said, that looks simple. I wrote the answer because I'm from a small school, and I give him the answer. He looked at it and grinned, started here, went here, 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 and he said, damn. He said, I've asked that more than 100 times. Your first one got it right. So I knew that small school is good. So no matter where you go to school, it's in what's in your individual mind that counts. Believe in yourself. When how I got into taking the wheel count was, we went to a meeting. As many people as here, I think, were there. And the director at the podium said, hey, he said, we have a problem. We have to navigate on the moon. Can anybody build a navigator for 10 pounds? One person raised their hand. That's how I got the job. Thank you.
All right. Thank you, everybody. So we are going to go ahead and get into the questions that you all have. So I'm going to start with Penny. Hello again, Penny. All right, and then Vince. Vince, okay. So I'm looking to see who on this side, who has the first question of the night. Raise your hand, please. Penny, please select someone. Please tell us your name, your team, and your question.
Hello, my name's Amanda Adney. I'm from Southwestern Oklahoma State University. And my question is what, if any, part of the development of the Moonbuggy did interns have?
What, if any, part of the Moonbuggy development did the interns have? Were there interns involved in the development of the Lunar Rover? Did you have young interns?
No, we did not. One of the secrets to doing this job in 17 and a half months was we needed some pretty experienced people. In any field that they were contributing in, they needed to be somewhat experienced. And the interns would not have, it would have been a great experience for them, but they couldn't have contributed to making this thing happen in the 17 and a half months.
Thank you.
Thank you. Okay, Vince, question for over here. Do we have a question for over here? Vince?
Hi, Alec Lindman from Rhodes College.
Can you speak up and speak slowly? We have the inspiration of the Space Camp kids next to us, so.
True. Certainly. Alec Lindman from Rhodes College in Memphis, Tennessee.
He's from Rhodes.
And my question is, how did what you learned about the dust and how it adhered to the buggy influence what you did in subsequent missions after the first rover mission? And how do you see that playing into the design of new rovers and mining machines and spacesuits for going back to the moon?
This one's for you. The question is, what did you learn about the lunar dust and how it adheres to the rover? And what did you learn from the first mission and then the subsequent missions that would be able to be passed on to any future missions on the moon?
Well, we actually started thinking about lunar dust about 1967 before we even landed on the moon. And we knew the fact that dust was a material that was it was very crushed rock, basically, because the moon continually gets bombarded by meteoroids, and therefore it's like when you garden the soil. Every time you garden the soil with a tiller, every particle gets smaller and smaller and smaller. So we knew the particle size were very small, and the fact they were very clean means they would probably attract electrostatically to the spacesuit itself. But we couldn't prove that, and we found out right quick on Apollo 11 when it landed, we had a problem with dust. And that was our problem. How are we going to get rid of this dust? And how are we going to take care of the dust with our rover? Because the rover is going to be tearing up the soil, and it's going to produce dust. So we did a lot of work coming up with an idea of fenders for the rover. And the idea of the fenders was to mitigate the dust movement. And the idea we came up with that was to actually fly a parabolic flight path with a device with a rover wheel and soil interaction, so we could actually see where the soil went when the wheel was rotating. And we found out very quickly we needed fenders because in the lunar environment, when the rover is running, it throws the soil, since it does pick up the soil because it does penetrate in the soil, it does pick up the soil and it tends to throw it out. And on the Earth, if you run the vehicle, it throws it like that, straight out. But on the moon, it throws it up and it comes down. So that's why we had to put the fenders on.
Yep. I can add to what Skeet said there that the fenders did help, but the basic problem, we made a mistake. We had a lot of studies about how you could remove dust here on the Earth, and it just doesn't work the same way on the moon. There's an electrostatic charge on there. And the other problem was we had one single dust brush that they cleaned everything with, so the bristles just had the dust in it, and we just pushed the dust around, and it caused our radiators to run hot. And so we tried, and you'll even see on Apollo 16 and 17, they knocked off the fenders that Skeet's talking about, and gave even more dust. They did fix it on Apollo 17, but we still had a lot of trouble with dust.
Okay, Penny, if we can have a question up front this time. Okay, from over here, a question.
Oh, hold on. I saw one over here.
You
did.
All
my
right,
alma
go
mater,
ahead.
the Colorado School of Mines, is sitting right up here,
Oh.
and I am giving them favoritism.
Yes, she's an alum. She's an alum.
Thank you, Penny.
Bias alert.
All right, my name is Noah Langford. I'm from the Colorado School of Mines. And I was wondering, from a materials science perspective, what considerations, other than weight and cost, did you have to factor into material selection for the rover?
So, from a materials science perspective and cost, how did that affect the materials that you chose to construct the rover? Who would like to take that? No one would like to take that. Maybe the program manager would like to take that. Program manager, sir?
We used the best materials engineers that we had in the country to help us select those materials that represented the best trade-off of weight, cost, and strength. Okay. So as a result, the wheel, for instance, the mesh on that is piano wire, which is a very strong steel. To cut down on the weight, the chevrons were made of titanium, and the aluminum itself was a common aluminum at the time, but it was machined down to eliminate every ounce of weight that we just absolutely didn't need. And we had the support of our materials laboratories here at Marshall Space Flight Center to help us make some of those decisions. that answer your question?
Excellent. All right. Vince, your turn from over here, please.
Hello. Hello, my name is John Sandusky, and I am.
Can't hear you.
We must speak into the mic.
Speaking
and-
into the mic now.
Yes, like
Okay.
this, and slowly.
My name is Jon Sandusky from the Academy of Arts, Careers, and Technology. We're team number 7, and I've actually got 3 questions.
3 questions.
Three
You have an
questions.
initial question with a follow-up, and then another follow-up.
You got it.
All right.
Okay.
Question 1.
Question number 1 is
Cheater. But go ahead.
is from myself and my teammate and friend Jason Christensen here.
No, that's how you're going to justify that. I got you. Go ahead.
And it is, could you explain what the function of the harmonic balancers were on the initial Moonbuggy?
Can they explain the result of the harmonic drive in the motor? Was that the question?
Yes, the usage of it.
So you want to know how the harmonic drive in the motor in the wheel operates. Is that correct?
Yes.
Okay. So can someone explain you want to do that, Ron?
I can do it. I was first asked, did any of y'all look at the website, the presentation I put on there for y'all to study? Because it's got the harmonic drive in there. The harmonic drive came from the United Shoe Machinery, and they did that actually on big coal mining operations. It's a system there where you have a flex spline on the outer ring, and then you've got a cam, got 3 different rotating members inside. You've always got a change in the number of teeth that are contacting, and it sets up a wave inside, a harmonic drive. They really hum. The motors really hum. The drive system really hummed if you listen to it. Of course, there's no sound on the moon. If you connect, that's the follow-up question. There's no sound on the moon, but that was what the harmonic drive, sealed up system, so we could keep down the dust that Skeet talked about. It was totally sealed. Had nitrogen gas in there and Krytox. We had Krytox lubricant inside.
And as I recall, this Rover over here, every wheel has a harmonic drive on it. So if you want to see harmonic drive, this Rover has it.
You have to have X-ray. You have to have X-ray vision to see inside.
Yeah. All right. So,
and that did
follow-up question 1.
Yes.
Okay. Go ahead.
That did actually answer my second follow-up question about the
okay.
flexible splines. But for my third question is, how did you prepare or develop the suspension system to account for such a dramatic change in the environment? Because I remember in the video he said that the suspension was actually it worked really well.
Okay. So if I can, you remember that picture of this Rover? Can you put that up during this question? So the question is, how did you all develop the Rover suspension system to account for the lunar environment? That pretty much gets it? That pretty much gets it? Okay. So we need somebody to tell us about the the LRV suspension system. And we're going to put the picture of that Rover up here in just a second. You remember the picture with the truck? You remember the truck? Right. That is that Rover. So that's cool, right? So, okay, go ahead. Who's going to take it?
Unfortunately, our structural guy, Denny Cross, couldn't come. And by the way, I wanted to apologize. This is a lesson for y'all. We did not fully work out with the people. This noise next door was not in our plan. I apologize. It's just a lesson for y'all. You've got to look into every detail when you're doing something. And we did. That's one thing that slipped by us. I'm sorry, but I can't hardly hear myself. I know y'all are having trouble. I'm sorry. But basically, the suspension system, it's got a lot of features in there that y'all need to study up on. And the book's good at talking about that, as well as the presentation I put on the website. There's torsion bars in there. There's suspension that hooks up to the drive system. It's just hard to describe it all to you. And Denny could do a better job. I'm sorry, but he couldn't come. We tried.
Okay, Penny.
We have a young lady over here who is very anxious to ask a question.
My name is Lacey Lamb from Southwestern Oklahoma State University, and I have somewhat of a personal question that is, sorry, But my question is, what was it like taking a dream and an idea that would be the heart of the mission and making it a reality? And what was it like with all of the pressure of this mission riding pretty much on just you guys alone?
Okay, I'm going to try to get this for our rover for our pioneers that are a little hard of hearing. So we're going to work this together. You ready? Okay. What was it like to be able to do such an important thing for you all on a personal basis? This was the heart and soul of the J Series missions for all intents and purposes, right? I got that part. So I want to know how that was. And then the pressure question part of it is, and how did you handle the pressure of the 17 months from the word go to getting her done and successfully wowing the world? Is that pretty much it?
Yes, that is pretty much it.
Okay. All right. All right. I think you got it.
I can answer the second half of the question. What we did in order to meet that 17 and a half month thing, obviously, it was a great deal of stress on us at the time. So we pulled out all the tools of experience that we had in the past on the F1, on the J2, and anything else that we were working on. We used all the tools that we could fall back on, which basically said, how can we make this job be accomplished in a short period of time? Now, the way the government normally gives a contract out and has them bid on it is that we establish a set of specifications for them to meet. They come up with a design. They study it in a phase A and then a phase B, and they come up with this design and they bid the job with their design to meet that specification. In the past, and that was my experience on the F1 engine, you look at those drawings, we had our technical teams at the center look at the drawings, you agree that this looks like it will work, and you accept that package as the starting point of the contract. And what happens at that point is, as the contractor begins to perform, he runs into problems, and he says, oh, this design isn't going to work in this area, or I don't have the tooling necessary to do this job. And so they turn around and they come in with a change request to the specifications. And so again, that goes through an evaluation period with the engineers at the Marshall Space Flight Center or the Army, and we decide whether or not we want to make that change for real. And if we do, we then authorize the contractor to make the change. Well, along with that authorization comes money, comes fee, and comes a negotiation that ties up our technical people and our program management people. All of this takes time. On the F1 engine, we maybe had something like 700 changes in the 6 years of that program. Well, I remembered this, and on the Lunar Roving Vehicle, we said, look, we're not going to do it this way. We don't have the time to do it this way. So we came up with what we called a performance spec. We said, these are the things this vehicle is likely to have to do on the moon. It has to go into potholes that are 2 feet wide and 1 foot deep. It's got to operate in a sandy, dusty environment. It's got to operate at temperatures of plus or minus 250 degrees on the lunar surface, all right? We left it up to the contractor to work the design in that area, all right? Now, he had to prove that it would meet those requirements, and we left him alone. As a result, on the Lunar Roving Vehicle contract with the Boeing company, we only had a total of 8 changes we had to negotiate. I can't tell you how many man-hours we saved of the technical team of the contractor as well as the NASA people, because we didn't have to review all of these change requests and send them through procurement and send them through legal, and et cetera, all right? So that was the technique, the management technique that I used on the LRV to save the time. That was one of the things. So it was the use of the performance-type contract as opposed to buying his detail engineering drawings to start with and then making changes to them as we grew. Okay? Now, it was a tough job, okay? But it was a slightly different managerial approach, and that certainly helped. I hope I answered your question.
Okay, I put up with the heart part. Does anybody have any kind of personal observation, any kind of, man, I can't believe we're doing this? Ron, didn't you have some kind of thought about that the other day where you were talking about that?
I guess I've been asked this question a lot about the pressure. Do we felt like we were under pressure? And I was just talking to Bob. No, I don't think it was pressure as much as, like Sonny says, you don't change your requirements, because I've been involved in a lot of government programs where when I went to work on the space station, when I left there, they were on change order number 5,500. 5,500. Think about that for a minute. That's unbelievable. And you got to believe the cost was great. And us, like Sonny says, we just stuck our mind to what we believed would work and crossed our fingers to some extent. No, we did a lot of testing. I want to express to y'all, we did an awful lot of testing. I'm amazed, but what Burke's probably referring to is, I'm amazed at how much testing we did. A lot of time spent in Seattle, Kent, Washington. Bob's been there many times. But I've been asked that question. Now, I don't think the pressure was there. I will tell you that out there at NASA, for the first mission, we actually had trailers out there because we thought we were going to be there 24 hours. But then we gave up the trailer. After the first rover worked, hey, the trailers didn't show up anymore. And people often ask also, hey, did you make any changes? No, there were not any real changes, because you got to remember, we went from 4-month centers between the missions up to 8-month centers. That meant 8 months between the different missions until they killed off Apollo 20, 19, and 18. And the point there is that in that 8 months, there wasn't really time to do drastic changes. And there was no indication from the astronauts that everything, like Mike is saying, everything worked fairly well. The seat belts, yeah, he had some trouble there. Some grief there. But they fixed that, we fixed that. And that'd be about the only thing I can think of that changed between Apollo 15 and Apollo 16. You think of anything else, Skeet? I mean, or Mike?
Can't think of anything
I think we scrubbed, maybe that's the wrong word. We did enough, what do you call it? Looking at Apollo 15, the manned systems, the crew systems, very thoroughly before we went ahead with Apollo 16. We flew quite a few zero-G flights testing the new seatbelt before Apollo 16 flew. And we knew we had to do it right because the astronauts that were already selected for the last few missions wanted to be sure that they can buckle and unbuckle those seatbelts and get in and out of the LRV. Not only did the commander who did the driving of the LRV have his pilot with him, sitting in that seat next to him. On Apollo 15, the name of the pilot who flew on Apollo 15 and rode on the LRV with Dave Scott was having a very hard time with the seatbelt situation. And not only did Dave Scott have to take care of his own problems, he had to help the name of the astronaut name?
Jim Irwin.
Jim Irwin, that's right. He was an Air Force officer. He passed away a few years ago. He was there trying to help him. So we made sure that that particular problem, the seating and the seat belts was thoroughly looked at, redesigned, tested, and we didn't think the crew of Apollo 16 was going to have any more problems. And they didn't. 16 and 17 were fine. We didn't have any complaints about that part of the LRV.
Okay, competitors.
One last
and those competitors at the Rover. We have time for 2 more competitor questions, okay? So here we go. Vince?
Hey, how's it going? My name's Husam Wadi. I'm from the Cape Girardeau Career and Technology Center. Now, my question for the panel is...
All right, you're going to have to speak up like me and speak slowly.
Okay. So, my question is, today's technology hasn't, within the past 40 years, the technology hasn't changed too much, but if you could change one thing about the Moonbuggy with today's technology, what would it be?
If you could change one thing about the Lunar Rover, what would it be?
When we sat down after Apollo 17, Hugh Campbell, my mentor, and I, we looked back, and this is not Bob's fault, the thermal fault, the team's fault. We severely regretted the astronaut time we had spent asking them to keep brushing the radiators and to clean up. We wish we'd have had an ammonia boiler system or some kind of sealed up system. We just didn't have the weight. As John said there, he got 10 pounds, we got 10 pounds for thermal. But we worked it out, and we got it done. We turned batteries off when they got hot. We did things. We opened up covers to let the heat radiate as much as it would. But we did have severe regrets. You talked about regrets there. That was a regret that we honestly sat there, and you lick your wounds when it's all over. You feel a great sense of accomplishment, like Sonny said, but you do have your regrets. And that was one of them, that we would have done things differently. We just didn't have the weight.
I'd put a telemetry system on it, like some of the ones I've seen walking around today. Well, yeah, that's some technology that we could have very nicely used on the LRV program.
That's cool. So before we get to the last question, there's something that I want to bring up for all of your benefit that you may or may not be aware of. Ron Creel, I need you to talk about this briefly, but I didn't see this. I didn't see it today, but the course still goes by the lunar module, right? You guys ride through the lunar module area. Ron, yeah, we've got a picture of that. You got that picture of Ron doing some work.
The form factometer. The form factometer.
The form factometer. So
anybody here know what a form factometer is? We use geometric devices, and next chart. Yeah, that's me out here. I called up. We only had one lunar module in the city of Huntsville, and it was out here at the Space and Rocket Center. There's one that you went driving by today, and so I called up Ed Buckby, and he let me come out here. We had a device that's a little hemisphere that you can sit down, and if you take a picture of it, it shows you it's gradated on the outside of it. You can figure out what the form factor, the view factor is from different surfaces to the other ones. And we figured out after Apollo 16 that they were parked too close to the lunar module, and then we used that form factometer data to determine where they should park it the next time out. That was a minor effect compared to the dust effect, but it did block your capability of the radiator being able to get its energy out to space.
So all right, so here's the cool part, right? I mean, how many people knew that your course that you're riding on, the Great Moonbuggy Race, was actually used to solve a problem with the real lunar rover? Anybody know that? You knew that, cheater. Anybody else know that? I mean, that is cool. I mean, think about it. You guys are doing this really cool stuff with Moonbuggy, and yet you're going over the very historical place where Ron had to fix a serious problem with the thermal system. I mean, that's pretty darn cool. All right, who's got the last question?
I've got the last question with this well-dressed gentleman right here.
My name is Jake Potter from Virginia City High School.
Can't hear you.
My name is Jake Potter from Virginia City High School.
Dave Potter, Virginia City High School.
And my question is, emotionally, what impact did this have on friends and family close to you all at the time? Because today, you are all considered heroes.
What was the emotional factors on you all at the time with your family and friends as you were working the program under these tight guidelines, as today you are now considered heroes? Who wants that one? Well, everybody's scared to come for that one. Oh, here we go.
Well, I don't know about the rest up here, but it cost me my marriage. My wife couldn't take all the TDY that I was on, and she wanted a divorce, and she wouldn't take no for an answer.
Anybody else want to tackle that one? That was a tough one. Okay, that was kind of a, all right. All right,
Hey,
here's one. Here's one more.
Hey, how's this work? I would just say that it depends. Now, in my particular case, why most of my friends knew that I was working on some kind of program, they didn't really make any difference what it was because that's what I was working on. My wife is one of those ladies who can make do with whatever. And so we had these 3 little kids, and she and the 3 little kids did everything they always do while I went to work, no matter whether it was all day or all night or some of both. So it depends on how strong is your marriage and how good your family is, and if they're good enough like mine, no emotional problems whatsoever. Got tired, but that's all.
I had a slightly different experience than Mike's. I guess I spent a lot of nights awake also, worrying about the various problems and meetings we had. But my only son was born in February of the year that we launched during the qualification period in Seattle of the vehicle, flight qualification. So that was a very happy time for us. And my wife lived through all of that, those early days and all of those many, many meetings and many long hours, and the sweat and worry. And she was fully supportive of it. But I didn't have to travel as much as Mike did, so that might have had something to do with it.
Okay. I want to thank all the competitors for bringing your questions forward. Those who got their questions asked are in the hunt for the book. Anyone else, their competitors, that have questions that they would like the Rover Pioneers to answer and have published on the NASA website, please get your cards with that information that it would be on it as if you were asking them the question to Penny or Vince. And the Rovers have agreed to try to do their best to answer your questions and get them posted with the answers. So I'd like to turn this over to social media. Are you there? There's some that are still here. Okay, so Penny, let's find ourselves, Vince, let's find ourselves a social media question. Who's got a question from social media?
Thank you. Good evening. My name is Jon Knickrehm. I have a comment in the question. Despite the noise next door, let's not forget we might be planting 6 seeds over there. They're going to show up at one of these panels one day. So I think it's very exciting to see all these children and all these young adults competing this weekend. I think it's great. So thank you all for all your work.
That was a good comment. Thank you for that comment.
My question for the panel is, according to the Lunar Rover Operations Handbook, the wheel encoders would send 9 pulses back to the control system, or back to the central computer, if you will, in order to measure the rotation of the wheels. I'm curious as to why there were 9 pulses only and not 360 or some larger number that might provide a higher resolution.
So the question is, why did the Lunar Rover wheel have 9 pulses being sent back to the computer in the console versus 360?
Unlike today's computers, the ones we had then were not very fast, and the ones we could afford to send to the moon were even slower. And so you had to limit how much data you could put through there to make sure you could vector it properly, and we found that that was adequate to give the accuracy we had to have, so why not?
Conservation of energy.
Do we have any more? That's good, thank you. Do we have any more questions? We do.
Hi, my name is Christina Meister with NASA Social. I just want to say it's been really great on our behalf to have all of you here. It's been such an inspiration to see everyone who's interested in STEM, and obviously to have these heroes of mine and of ours to speak with us tonight. So my question is, so far at NASA Marshall, I have learned that it truly takes a village to operate a successful operation. It also takes courage, leadership, camaraderie, and sometimes a sense of humor. As the next group of potential leaders in science and technology, what would you say are the key traits of a successful, purposeful, and joyful career? And what advice do you have for this next generation?
I do. I understand the question. What's it take to have it? What does it take to have a successful career in your business? Is that essentially the question? And what advice do you have to these folks as they're looking towards embarking on their careers to do the kinds of great work that you all did? That's kind of a paraphrase of the question.
Work hard. Work hard. And believe in what you're doing. You know, it's not just enough to have a job to make money, but have a job that you feel like you're making a contribution. And that was the beauty of working out here at Marshall Space Flight Center and the Von Braun philosophy of management. You felt like you were making a contribution, even if you were just doing a simple little drawing for them or answering a question. So work hard and study. Get your degree and come apply for a job at NASA.
Also, it doesn't hurt to be working on a program that's 100% approved funding-wise, and you got Congress behind you, and all the monetary requirements will be met. You feel like you're not wasting your time, like things are going on right now at NASA. They don't know whether that program is going to take 10 years or 20 years or whether it's going to be canceled. We knew ours, since JFK was the one that initiated it, we knew we were going to do or die. And that inspired us. That's all I can tell you about that part of it.
When you're sure of your information, you have made a good understanding what you have. Stand your ground. Stand up for what you believe in, but be right when you stand up.
That's very good advice. Thanks.
I think one of the big things is that believing in what you're doing and don't be afraid to fail. If you don't fail, you ain't ever going to get anywhere. The thing to do is to have your failures, fix them up, and come back and stay after it. It takes a long time, and it hurts, but that's the way it goes.
Hey, Ron. So I promised NASA, and I promised the Rovers that we'd finish on time, and I broke my promise by 5 minutes. I want to wrap up by thanking our volunteers, and I'm going to identify them real quick. I may slaughter some of their names, but I'll do the best I can. Vince Vazzo, our mic man. Penny the Force Pettigrew. Mike McKenna, the man who put up all the beautiful graphs and pictures. And the folks that help feed you, who are NASA interns. Where's my intern question person? There's our interns. Joanne Gunn, Alex Saffer, Jeff Ocasio, and Geraldo Alvarez. I want to thank NASA and the U.S. Space and Rocket Center for allowing us to have this and bring this to you today. Social media, thank you for being here. And I want to thank the pioneers. I think this has just been fabulous. I'm going to tell on him a little bit. Ron Creel up here is the youngest at 66 years old. So please keep that in mind as you talk to these folks. They're here on their own personal time. They came here at great effort and great personal sacrifice, and they're here for you, and they care about you, and they want you to be successful. And I have a right here. This is Sonny's, but I want to show this to you. We have 10 more of these, and we would be happy for you to take them home with you. So if you would like to take one back to your hotel room or your other teammates, they're up and ready for you. Hang on, don't go yet. I see the guys that like to eat. Hang on. So don't do that yet. Please clean up your tables also on the way out. But the last thing I want to leave with you again is I want to thank this panel for coming up here, for doing this very much.
I have one last comment I'd like to make. If you can still have the patience to listen to us. We've gotten a lot of accolades up here, and they're very well deserved for these fellas. But I have to tell you, as the team leader of the Lunar Roving Vehicle project, as well as the F1 and the J2 for a couple of years, I have to tell you that it isn't just the project manager that makes it successful. It's the effort of the team, and you've already found that out today, and you'll find out tomorrow. It's your team effort that makes for the success. And don't ever forget that. It's not a one-man show. Okay?
That concludes our program. Thank you for coming. If you'd clean up trash cans over there, and if you'd like to come visit with the Lunar Pioneers, they'd love to see you and talk to you.